Okay, so we noticed that when we tried to apply the sort of sophisticated version of the relativistic energy, we ended up at the Klein-Gordon equation, right? So Kg, and solutions are of the type, normalization factor. We have values of momentum that we sum over. We have weights for each momentum, and then we have these wave solutions. These can be really, we found positive or negative solutions there for the frequencies, for the energies, because of the second order derivative in time. That looks like a problem. So we notice experimentally that we have, so we're looking for clues to see how to proceed. We know of the existence of particle-antiparticle pairs created. And so there's a kind of opposite property here that we might that might allow us to reinterpret things. Instead of having negative energies, we have all positive energies, but we think of some feature of this that allows us to play this game where the opposite nature of the quantity allows us to interpret the existence of antiparticles. So we're sort of thinking of getting rid of the negative energies and making them positive. We need to figure out how to get a spectrum of energies here. So notice that there's no clear path forward. And then we'll see that causality. So negative energies sort of reinterpreted, always in the context of this solution, because that's the equation that we ended up with. But just doing this doesn't give us any clear path forward. We have to reinterpret this. Then we have issues with causality. We looked at that already. It's not immediately obvious that when you do the basic project of the Schrödinger quantum physics approach, basically says that this is asking, how does the wave function change with time everywhere? And the answer is it depends on the energy. And that's a special relativistic violation that leads to a special relativistic violation of causality, as we sort of saw. But it's not sort of direct, because after all, this is not classical physics. We don't have exact positions of particles at given moments of time. And so we saw how to interpret causality violation by using psi star. We also noticed that we don't have a decent interpretation of the relativistic version of the probability density. That's going to have to be reinterpreted. But let's notice that if we write this equation in this way, we can maybe see some parallels and some clues to move forward. So e to the I PR, then let's write the rest of this and the time-dependent part as that. Let's write it like that. And let's apply the Klein-Gordon equation to this. Right, so two derivatives in time, and then we have minus del squared acting on this object. So we end up with two derivatives of this quantity, right? Plus, we have a minus sign here, but we have two derivatives in this kind of a thing, which brings out a minus p squared. So we have a c squared p squared quantity. And then we have the last term. I multiply the constants out that were in front of the two derivatives in t term. So we had an h bar squared over c squared there. We have the phi of p and t, and this is equal to 0. And so looking at this, we see that there's an operator acting on this. So we can rewrite this as two derivatives in time plus a c squared momentum squared plus m squared c to the fourth over h bar squared term times phi. All right, so this term obeys this equation, and this equation is nothing more than the equation for the simple harmonic oscillator, right? So two derivatives in time proportional to minus some quantity times the function itself. That's the simple harmonic oscillator. We know how to solve that. So what this is telling us is that when we're doing special relativity plus quantum mechanics, we end up with the free particle, which is what we're trying to model. The free particle that obeys both special relativity and quantum mechanics. This is, in some sense, like the simple harmonic oscillator. So we have a formalism for the simple harmonic oscillator. We can take that and let it guide us. And perhaps the most difficult thing to be able to resolve is this issue of causality. So we're going to have to be careful there, and this is arguably going to lead us to the sort of strangest kind of object in order to make this come together. But notice that there is no direct, clear path forward. We have to do it looks like we have some flexibility in applying the principles.